In our most recent videos, we've been talking about rings, algebras with two operations on them, and we've also introduced the concept of subrings, quotient rings, ideals. Well, we're going to bring all those things together today by introducing the notion of a ring homomorphism, and all of these earlier topics about rings are going to fit together under this umbrella. Let's go to the whiteboard. We're going to start with an example, and it's a familiar one that we've looked at before in the context of groups. And I want to recall the function that we had introduced several videos back, a function h that's going from the integers under addition to z2 under mod 2 arithmetic. And we notice that this function that I have defined here is in fact a group homomorphism. And just to refresh your memory a little bit, we went through several cases. We said, well, let's see, if A and B are both even, then A plus B is going to be even, and so H is going to take A plus B to 0. Well, H of A is going to be 0 and H of B is going to be 0, again, because A and B are both even. And if I add 0 and 0 together, I get 0. So whether I add first in Z or look at the image in Z2 and then do my addition, I get the same result. Similarly, if A and B were both odd, I'm going to get an even number, but 1 plus 1 is 0. And so H of an even number being 0 and 1 plus 1 being 0 also gives us the same value whenever I do my addition, either first in Z or later in Z2. And similarly, if A were even and B were odd, I'm going to have an odd number that H is sending over to Z2. So that's going to go to 1, but an even and an odd is going to go to, it's going to go to 0 plus 1, which is 1. So again, we get the same value. So this is a homomorphism with respect to the operation of addition. What I want to ask is, does H also preserve multiplication? Well, let's do a similar check. If I multiply two even numbers together, I'm going to get an even number. So this is going to be 0, but 0 times 0 is 0 as well. So that works. If I multiply two odd numbers together, I get an odd number. So this is going to get sent to 1. But H of A is 1 and H of B is 1. And whenever I multiply 1 by 1, I get 1 in Z2. And then finally, if I had an even and an odd, then whenever I multiply those together, I'm going to get an even number. But 0 times 1 is going to be 0. So I'm going to get 0 whether I do my multiplication first and then look at the image, or do my images first and then multiply. And so sure enough, H does in fact preserve multiplication. And that's exactly what we mean whenever we say that H is a ring homomorphism. It's the same notion really as a group homomorphism, except, well, first of all, we're working with rings, and second of all, both of the operations are preserved under the function. Okay, so that leads us to the definition, right? If I have two rings and a function between them that preserves both the addition in my domain ring and the multiplication in my domain ring, then I'm going to call that structure, that function, a ring homomorphism. You might have guessed that if H is also bijective, then we're going to call H, well, not just a homomorphism, but if it preserves both operations and H is bijective, we're not going to be able to distinguish algebraically any difference in the structure of those rings, and we're going to call that a ring isomorphism, right? So these are all terms you're familiar with in the group setting, and they carry over into rings as well. So here's another example, a more general one. So let's look at the function from z to not z2 this time, but well, it could be z2, but zn for any positive integer n. And we're going to define our function to be, we're going to send a to a mod n. You might recognize that whenever n is 2, this is exactly the function that we looked at before. We're just expressing it a little bit differently. And that turns out to be a ring homomorphism for every n. The proof of that is a homework exercise, and I recommend that you use Theorem 24 from our notes whenever you prove it. Okay, here's another example. Let's let h be the function from the integers onto z2 again, and we'll define that just as we defined it before, and notice that we could have used the format that we just spoke of in the more general setting. What's the vanishing set of h? Think about that for just 3 seconds. Did you get it? So do you remember what the vanishing set is, right? That's the subset of z that h sends to the identity element of, in this case, of z2, right? So it's going to be a subset of z, and it's all of those elements that get sent to the identity element. In this case, we're representing that as 0 in z2. Well, the function actually tells us very explicitly what that's going to be. We're going to send the elements. We're going to send elements to 0 if those elements are even. And so it's the even numbers that form the vanishing set of h. So there we go. So the even numbers is the vanishing set of h. We know that the even numbers absorb products in z. We've seen this. We saw that in, I believe, our last video. And so we call E an ideal of z. Now let's think about this for just a moment. How many elements are going to be in the quotient ring z mod E? Keep in mind, z mod E makes sense because E absorbs products, right? We've seen that. That was exactly the additional condition we needed on a subring in order to guarantee that the quotient ring existed. So this makes sense. How many elements are in it? What are those elements? And how is this quotient ring related to Z2? I want you to spend just a little bit of time thinking about that. So if you'd pause the video for just a moment, I'll be here whenever you get back.
Let's all go to the lobby. Let's all go to the lobby. Let's all go to the lobby to get ourselves a treat.
Okay, how'd you do? Here are the answers I got. Well, Z mod E is a 2-element set. They are going to be the cosets of E, and I could represent those as 0 plus Z. I could have also just written Z. It's the same set. And 1 plus Z. So let's see, what kind of things are in 0 plus Z? Well, that would include 0, 2, -2, 4, -4. In fact, all the even numbers are going to be in this coset. All the odd numbers are going to be in 1 plus Z. And so if I wrote n plus Z, which I could certainly do, that would be the coset that contains n. Well, for example, 3 plus Z, the coset that contains 3, is just another way of writing 1 plus Z. So all the cosets can be expressed as either 0 plus Z or 1 plus Z. what else? Well, if I consider the function that sends members of Z mod E to Z2, that's defined by, well, the very natural way, let's send n plus Z to n mod 2. Of course, that's exactly how we defined H, isn't it? Right? F or H sends A to A mod 2. So H of n is n mod 2. So in other words, F of n plus Z is just H of n. If I consider that, that turns out to be an isomorphism, right? It's going to send 0 plus Z to 0. It's going to send 1 plus Z to 1. And well, at that point, I've exhausted the members of Z mod E, and it's very easy to show that that function is an isomorphism. I can actually summarize all of this information in one diagram. And here it is. We've not looked at this diagram before, but it's a pretty common way of expressing all of this information in a compact setting. So we're starting with our domain set Z, our codomain Z2. H is a homomorphism, a surjective homomorphism. I was leaving that out. We're only considering surjections right now. So H is a surjective homomorphism. Then it turns out that in this case, the vanishing set E is an ideal, and so Z mod E is a ring, and it's isomorphic, using this isomorphism right here, it's isomorphic to Z2. Now I also have this function phi that's going from Z to Z mod E, and what that's referring to is the function that sends each n in Z to the coset that contains n. Can you show that that phi is a homomorphism? Stop the video for just a moment and verify that you can show that phi is a homomorphism. I'll wait here. Okay, so I will presume that you were successful at that. And I want to note that all of these results, everything we've talked about so far, generalize to all ring homomorphisms. Here's a theorem. Let's let H from some ring R to some ring S be a ring homomorphism that is surjective. Then we have a number of things that are true. First of all, the vanishing set, and I'm going to call the vanishing set K of H, is an ideal of R. Incidentally, I didn't mention this whenever we were talking about groups, but if anyone takes a course in abstract algebra beyond this one, you'll probably want to know that the traditional name for what I'm calling the vanishing set is the kernel of the homomorphism. I'm going to continue to use vanishing set, but I'm going to use K to remind me that kernel is the term that is traditionally used. You've encountered that term before, actually, whenever you were studying linear algebra. In fact, it meant exactly the same thing. The kernel of a linear transformation was the set of was the subset of the domain that the linear transformation sent to the zero element in the codomain. So vanishing set would have worked there as well. I just think the term vanishing set is a whole lot more descriptive. Secondly, since K is an ideal of R, I can look at the quotient ring R mod K, and it turns out that the function that sends each coset R plus K to what the homomorphism set R to, that turns out to be, first of all, a well-defined function. It's important to notice that first. You may recall that we had to spend a little bit of time talking about that whenever we were looking at group homomorphisms. But not only that, not only is it a well-defined function, but it turns out to be an isomorphism. And so every time the quotient ring, the ring mod the vanishing set, is isomorphic to the codomain of H. Finally, the function that sends the ring to R mod K, to the set of cosets of the vanishing set, if I use the function that sends R to R plus K, that turns out to be a homomorphism every time. I'd like you to prove all of these for homework. So this theorem, just as important as the fundamental theorem of group homomorphisms was to groups, this is a very important theorem, and I'll bet you can guess what it's called.
Yes!
That's right. This theorem is called, not surprisingly, the fundamental theorem of ring homomorphisms. And you're going to prove it entirely on your own. I think you're equipped to do that. You're welcome to go back and look at the proof of the fundamental theorem of group homomorphisms. If you would like, I would encourage you not to go back right away. See how much of that you can do on your own and go back as you need to. So what this says is that every homomorphic image of a ring R is isomorphic to a quotient ring of R, right? In particular, it's the quotient ring of R mod the vanishing set, but let me just summarize it by saying that every homomorphic image of a ring R is isomorphic to a quotient ring, and every quotient ring of R is a homomorphic image of R, right? And so what that means is that the collection of homomorphic images of a ring and the collection of quotient rings of R are identical. There's so much more that I'd like to discuss with you. I'd like to talk about principal ideal domains, polynomial rings, fields. I'd like to eventually introduce a little bit of Galois theory to you. But unfortunately, we've run out of time. This seems an appropriate place to conclude our video series, and this will in fact be our final video. We're not going to meet again in this manner, and so I'm simply going to say, stay well, stay safe, so long.